Hi there, I'm Honor, and in this course we create a 3D game with physics using Three.js and Cannon.js. The game itself is very simple. We build a stack of boxes. Boxes are coming in from left and right, and you have to click when the incoming box is on top of the previous one. You have to be precise though, because the overhanging parts will fall down, and the surface you can place boxes on gets smaller and smaller. So that's our game. We will use Three.js to generate the graphics and Cannonjs to simulate the physics in this game. If you haven't used these libraries before, don't worry. This is an introductory course both for Three.js and Cannonjs. We will go through everything in detail. We go through how to set up the scene, how to add lights, how to set up the camera, and how to add animation and event handlers. And finally, we will add physics. The only thing you need to be familiar with is JavaScript. But we won't do anything crazy with that either. So if you have a basic understanding of JavaScript and you want to learn Three.js, then this is a good start. The whole game is only about 200 lines of code. So let's get into it. To generate graphics, we are using Three.js. Three.js is a library that uses WebGL under the hood and makes things much easier for us. We only have to put together some 3D objects in a scene, set up some lighting, a camera, and we are good to go. It's almost like playing with Lego. Let's start with a simple scene. We have a box in the middle of the screen, and that's it. We have to set up a few things here. First, we set up a scene containing the box, and we add some lights. Then we talk about different camera options and how to add the camera. And finally, we set up a renderer that renders the scene in the browser. Let's start with the scene. The scene is a container. We're going to add 3D objects and lights to this scene. The scene also has some properties you can set. You can set the background color, for instance, but we are good with the default black color. Then we add a mesh to the scene. A mesh is a combination of a geometry and a material. A geometry you can either build up from scratch or you can use a predefined one. Here we are using box geometry. We only have to set the width, height and depth of the box and that's it. Then we define a material. There are different material options. The main difference between most of them is how they react to light. The Mesh Lambert material is the simplest option that takes lights into consideration. In comparison, if we would use Mesh Basic material that doesn't care about lights, then our mesh would look like this. You don't see the edges of the box anymore. The box has the same color on every side. There are also more advanced materials that can look nicer and more realistic. They use more advanced calculations that can make our game relatively slower though. So for a minimal game like this, we are good with the Lambert material. Then we add lights. The Lambert material requires lights. If there wouldn't be any lights, the whole scene would remain in darkness. We add two lights, an ambient light and a directional light. First we add the ambient light. The ambient light is shining from every direction. We use it to have a base color for our shape. To set an ambient light, we set a color and an intensity. The color is usually white, but you can set any other color if you want. And the intensity is a number between 0 and 1. The two lights we will define will be used simultaneously, so you probably want the intensity to be around 0.5. The directional light has a similar setup, but it also has a position. And the position is a bit misleading here because it doesn't mean that the light is shining from that position. There are different lights for that. There is point light and spotlight that both have an actual position. The position of a directional light, though, serves as a direction of the light. The directional light is like the sun. The sun also has a position, but if you're walking around in your garden, then it doesn't really matter which end of your garden you are. The sun will shine at you the same angle. And that's what the directional light is doing. It shines to everything at the same angle from very far away. Here we set the position to be from above and shift it a bit along the x-axis as well. The y-axis has the highest value. This means that the top of the boxes receive the most light, so they are going to be the shiniest side of the boxes. The light is also moved a bit along the x-axis, so the right side of the box will also receive some light, but less. And because we don't move the light position along the z-axis, the front side of the box will not receive any light from this source. If there wouldn't be ambient light, the front side would remain in darkness. So we set up a mesh with geometry and material. We set up lights and we added all of them to the scene. We still need a camera to define how we look at this scene. There are two options here. There are perspective cameras and orthographic ones. Video games mostly use perspective cameras because how they work is closer to how you see things in real life. Things that are further away appear to be smaller, and things that are right in front of you are bigger. In this game though, we are going to use orthographic projection. With orthographic projections, things will have the same size no matter how far they are from the camera. It also doesn't distort the geometries. The parallel lines will remain in parallel. This will give our game a more minimal, geometric look. So how do we set up cameras? For both cameras, we have to define a view frustum. This is the region in the 3D space that is going to be projected to the screen. Just as a reference, this is how you can set up a perspective camera. In this figure, you can also see how the projection works. Everything within the view frustum is projected towards the viewpoint with a straight line. Things further away from the camera will appear smaller on the screen because the viewpoint can see them under a smaller angle. You need to define a field of view, which is the vertical angle from the viewpoint. Then you define an aspect ratio of the width and the height of the frame. If you fill the whole browser window and you want to keep its aspect ratio, then this is how you can do it. Then the last two parameters define how far the near and far planes are from the viewpoint. Things that are too close to the camera will be ignored, and things that are too far away will be ignored as well. Numbers here are a bit unrealistic. You want to have the near plane much closer to the viewpoint because you don't want to lose the objects in between. With this figure, I just wanted to showcase how the projection works. Then there's orthographic camera that we are actually going to use. Here we are not projecting things towards a single point, but towards a surface. Each projection line is in parallel. That's why it doesn't matter how far objects are from the camera, and that's why it doesn't distort geometries. For orthographic cameras, we have to define how far each plane is from the viewpoint. We define that the left plane is 5 units away to the left, and the right plane is 5 units away to the right, and so on. Here we are using the same units we were using when defining the size of the box. It doesn't matter if you're using small numbers or big numbers, you just need to be consistent in your own word. Regardless of what camera are you using, you also need to position it and set it in a direction. Because we are using an orthographic camera, the actual numbers here don't matter that much. The objects will appear the same size no matter how far they are from the camera. What matters though is their proportion. Here we are moving the camera with the same unit along every axis, then we look back to the 0, 0, 0 coordinate. Positioning an orthographic camera is like positioning a directional light. It's not the actual position that matters, but its direction. So we put together the scene and the camera. Now only the final piece is missing that renders the image into our browser. We define a WebGL renderer. This is the piece that is capable to render an actual image into an HTML canvas when we provide a scene and a camera. This is also the piece where we can set the actual size of this canvas. We set several sizes already for the box and when we place the camera. All these sizes were relative in our own word. The size we set here though is the size of the canvas in pixels as it appears in the browser. And finally, the last line here adds this rendered canvas to our HTML document. And that's all you need to render a box. It might seem a little too much for just a single box, but most of these things we only have to set up once. Most things we won't change at all as we're building this game. The lights, for instance, won't change at all. The camera will only move vertically as we're building our stack, and we want the camera to keep up with it. And we are going to add new boxes to the scene. But the other lines, like the renderer, won't change. Let's see now how can we go from one box to a game. In this phase, we add animation and event handling. In the first iteration, we go with the simplified version. The top-level box will move along the X or Z axis depending on its direction, and on click event, a new box is added to the top. In this phase, we don't care where the moving box stopped when we click the mouse. We don't care if it's overlapping the box underneath at all, therefore we don't cut the overhanging part either and nothing is falling down. As a start, let's restructure our code a bit. We move most of the code we had before into an init function. What we did before was mostly setting things up, and we only need to do this at the beginning. There are two changes though. One of that is that some of these objects will be globals. We want to have access to the camera, scene, and renderer in other parts of the game. We are going to move the camera as we are building the stack. We add new boxes to the scene, and we are going to re-render the whole scene at every animation frame and interaction. The second thing that changed is that we moved the code generating the box into a separate function. We create the foundation of our game here and add the first layer off-screen that we'll move in once the game has started. We are also going to call this function every time we add the new layer. This function only requires the X and Z position of the box. The Y position will be calculated automatically by this function. We also need to set the width and depth of the box. The width and depth will be smaller and smaller as we advance in the game, but the first two layers at this point will still have the full size. The height of the box is constant. As a fifth attribute, we also need to pass on a direction. This will say if the box will move along the x-axis or the z-axis. So how is it implemented? The addLayer function adds a new box not only to the scene but also to a global stack array. This is just a JavaScript array. There's nothing special or Three.js specific about it. We just want to have a reference for each layer. Later, when we add animation, we will look up the top layer in this array. When we detect if the two boxes are overlapping or not, we will find them in this array as well. And one other benefit of this array is that when we are adding a new layer, we can calculate the Y position of the box based on the length of this array. When we add the first item, this array is empty, so the box will be at position 0. Then when we add the second layer, the stack already has one item, so the box will be one box higher, and so on. The addLayer function uses the generateBox function to create a mesh. We are splitting this logic into two functions here because the addLayer function will have a pair. Later on, we will have an addOverhang function that also uses the generateBox function but behaves a bit differently. The generateBox function is pretty much the same code that we had before in our initial example. It creates a geometry and a material and adds them to the scene. There's a fun difference though in computing the color. We define the color by setting the hue, saturation, and lightness. The hue value will pick a color on the color wheel. We start at 30 degrees, and with every layer we add 4 degrees to it. This way, we end up with a gradient without too much code. We start at orange, then it turns into yellow, then green. The last thing to note here is that what we are pushing into this array is ultimately an object with 4 properties. One of the properties is called Three.js, containing the mesh. We could call this simply mesh, but later on, when we add physics with cannonjs, this object will be expanded, and I wanted to highlight the boundary between Three.js and cannonjs. The other 3 properties are values we are going to use during the game. we are going to use width and depth when checking if boxes are overlapping or not, and we are going to use direction when we move the top layer. Speaking of which, let's move on with event handling and animation. Let's introduce a new global for the status of the game. The GameStarted variable indicates whether the game is in initial state or if the game has already started. Then let's add an event listener for the click event. The click event can do two different things. If the game haven't even started, it starts the game. And if the game is on, then it stops the moving box and adds another layer. If the event listener finds that the game hasn't even started, then it starts the animation and sets the game started flag to true. It starts the animation by passing on a callback to the setAnimationLoop method of the renderer. This works in a very similar way how requestAnimationFrame works in JavaScript. The main difference is that the requestAnimationFrame function will only run once, and you have to keep calling it to have a loop. The setAnimationLoop though keeps on running the given function till we stop it explicitly. Now let's check what's happening inside of it. Inside the animation function, first we pick the top level stack item. We know its direction because we set the direction property in the addLayer function. The direction will be X or Z, stating that the box should move along either the X or the Z axis. So with this line, with every loop, we increase its position by a bit, either the X position or the Z position based on its direction. Then we also change the camera position, but this is conditional. The camera needs to keep up with the height of the stack, so we move it vertically as the stack grows. But we don't want it to move out of the picture. So we check if it's where it should be, and if it reached the correct position, then we don't move it anymore. And the last line here will re-render the whole scene again with every animation loop. Without this line, it doesn't matter what you change, nothing will be updated in the browser window. So this animation will move the box to infinity. And yes, in the video it's not actually moving because this is just a slideshow simulating the behavior of the game. But imagine that the box is moving at a constant speed. Then let's say, right on time, when the layer is right above the box below, you clicked the mouse. What's happening in this case? This triggers the other case of the event handler that stops the moving box and adds another layer. Actually, we don't stop the moving box. We just add the new box on top, and the next animation loop affects this new box from now on, because that's the one on top of the stack. So how do we add a new box? We need to calculate its position, its size, and its direction. The position and direction depend on the previous box. If the previous box was moving along the x-axis, this next one will move along the z-axis. If the previous moved along the z-axis, then this one will move along the x-axis. It's always switching. Similarly, the boxes always start at the -10 position. If they move along the x-axis, they will start at -10x. If they move along the z-axis, they will start at -10z. Then with these parameters, we call the addLayer function that will automatically place it one level higher and add it to the stack array. So the next time the animation loop is running and picking the top level item, it will pick this one. It will find that this one is moving along the z-axis, and it will increase its z position till infinity or till the next mouse click event. So that's the general idea of the game. The top level is always moving, and when you click, a new box is added that moves along the other axis. In the next step, we'll check after the mouse click if the moving box is overlapping or not the box below. And if it overlaps, then we split it into an overlapping part and an overhanging part that will fall down. We reached the first prototype of the game. Box is moving in from left and right, and the new box is added on mouse click. In this phase, we will do some calculations to see if the moving box is overlapping the one below or not, and if they overlap, then we split the box into two pieces. The one that overlaps and stays on top of the stack, and the one that overhangs and will eventually fall down. Let's play through this scenario. A box is moving along the x-axis, and a bit after they start to overlap, the player clicks the mouse. Now let's see this scenario from the front view. This is the part when the player clicks the mouse. Now we have to split the moving box into two pieces. The overlapping part will stay there, and the overhanging will fall down. I'm replaying this scenario because this is something we have to calculate ourselves. The falling part will be simulated by cannonjs, and it will not only move the box downwards, but it will simulate what happens if it falls on the lower level or if it hits the edge of a lower level and rolls down. But splitting the moving part into two pieces we have to do ourselves. So how do we do that? We are going to extend our event handler function. When we click the mouse, we don't simply add the new box that moves along the other axis, but we do a whole lot of other things as well. So let's say at this point you click the mouse. Let's walk through what's happening. First, we pick the two top-level boxes from the stack. We are going to compare these two. We also note in which direction the top-level box is moving. In this case, it will be the z-axis. Then we calculate the delta value between the two boxes. We get the x position of the boxes from the Three.js mesh and subtract one from the other. This will give us -10 in this case. It's easy to see that if the center of these boxes are 10 units away from each other, and the boxes have the same size, then the left side of these boxes are also 10 units away. This will give us the size of the overhanging part. The only conversion we have to do here is that we take the absolute value of the delta. The delta can be both a positive value or a negative value, depending on whether we stop the moving box too soon or too late. The size of the overhang though is always a positive value. We also know the size of the boxes. In case the box is moving along the x-axis, the relevant size is the width. If it would move along the z-axis, the relevant size would be its depth. Then, by subtracting these values, we get the overlap. If the overlap is more than 0, then we can go on with the next step. If it's not, that means we failed. Then we can stop the game by stopping the animation loop. But in this case, the two parts are overlapping, so let's see how to split the box into two parts. First, we calculate the new width and new height of the box. Only one of them is changing. As we are moving along the x-axis, the width of the box will take the size of the overlap, and the depth will remain the same as before. If we would have been moving along the z-axis, the opposite would have happened. Then we update our metadata in the object, because we are going to need it later. Then let's update the width of the box. We just calculated the new size of the box, but actually we are not going to use this value here. That's not how Three.js works. Instead of that, we can scale the mesh. So here we scale the x dimension of the mesh to the proportion of the new and the old size. This will change the size of the mesh, but it keeps the center at the same position. We also need to move the box. It might look like we need to move it with the overlap, and that would work in this case, but not in other cases. This is just a special case that you can see here on the slides, where two things have the same size. Instead of that, we have to move the center by half of the delta. In this figure, you can see that the x-coordinate of the overhanging part is halfway between the center of the two boxes. So with the scaling and the shift, we have the piece that stays on top of the stack. Before getting to the overhanging part, let's see how the next box is added to the game as a result of this click. We calculate the position of the next box in a similar way as we did before. One of the values is always -10, but the other value now is adjusting to the coordinate of the box that stays on top. The center of the box we just cut is at -5 on the x-axis, so the next box we add to the game will also have a -5 position on the x-axis. The width and depth will take the same values we just calculated. So ideally, if you click the right time in the next turn, these two boxes could fully overlap. And finally, the box is switching directions the same way it was before. And then we add this box with the addLayer function. Now let's also calculate the overhanging part. We calculate the position and size, then we call a function to render the actual box. We can quite easily get the distance between the center of the overlapping part and the center of the overhanging part. We know the size of both, so we just take half of both. This would always be a positive value, as both sizes are positive. But the shift can happen in both ways. If the click event happened too soon, then we have to subtract this value. And if it happened too late, then we have to add this value. So we multiply it with +1 or -1 depending on the sign of the delta. The sign function here is one of the less used utility functions in the math object. It returns +1, -1 or 0 depending on the value we pass on to it. Here the value of delta is negative, so ultimately we end up with -7.5. Then we calculate the x and z position of the overhanging box based on the overlapping box and this shift. One of these values will always stay the same as the overlapping part's position, and the other one will be adjusted by the shift. A similar thing is happening with the width and the height. In this case, as we are moving along the x-axis, the width will take the value of the overhanging size, and the depth will take the same value as the cut piece. If the movement would have happened along the z-axis, then the depth would have taken the overhanging size, and the width would have ended up the same as the other box. And finally, once we have the position and the size, we call a new function called addOverhang. This is a very similar function to addLayer. It generates a box and adds it to an array. Except here we don't add it to the stack array because we don't want to mess up how the y position is calculated for every added layer. Also, we calculate the y position a bit differently, as we don't want to move it one level higher, but we want to keep it on the same level. And overhanging parts don't have a direction, at least not one that we could use for anything. We don't want to figure out ourselves how to simulate gravity and what should happen when the falling pieces hit the edge of a lower level. Instead of that, we are going to use cannonjs to simulate physics. So let's look into how cannonjs works. We arrived to the final piece. We add physics with cannonjs. Three.js and cannonjs are two completely different things. Cannonjs is not an extension or plugin to Three.js, but a library on its own that simulates physics. And by simulating physics, I mean that it can tell you where the 3D objects should be in the 3D space, but it doesn't show them to you, it just gives you numbers. That's why we are using it in combination with Three.js. Three.js is the visual part. It renders the objects on the UI. Cannonjs is the brain that tells us how to manipulate objects defined with Three.js to look like they are obeying the laws of physics. Because they are two entirely different libraries, this also means that we have to set up our word twice. We have to set up everything first for Three.js and once for cannonjs. Then the general idea is that whenever we change something, we have to update both models, and before rendering the scene, we run the simulation of cannonjs and then sync the numbers it comes up with to Three.js. So let's go through step by step each piece we have to change. We start with the init function. We have to define a word for cannonjs as well. This is similar to the scene in Three.js. It's ultimately a container that will hold our boxes. Here we don't have too many things. Luckily we don't have lights, and we don't have a camera in this word. The important part though is that we are setting up gravity. Also note here that the word variable is global. We need to have access to it in other parts of the game. Then we want to make sure that what exists in Three.js exists in cannonjs as well. We update the generateBox function. We create a body in a similar way we create a mesh. It has a shape that is also going to be a box. But be aware that while it's a very similar looking thing, there's a major difference here. When you define a box in Three.js, you set its size. You set the width, height, and depth. But when you define a box in Cannon.js, you set the distance from its center to its sides. This ultimately means that you have to divide each dimension by 2. Then we also have to position this body the same way as we do with Three.js. Luckily, there's no difference there. Bodies in Cannon.js don't have a material because they are not visual, but we can set physical properties like mass. If we set a mass, then gravity will affect the body. If we set the mass to 0 though, then gravity won't affect it. Yet, it will still hold other objects that fall on top of it. So objects with 0 mass will be stationary objects in our space. We are going to have 2 cases. Boxes that are moving and the ones that stay on top of the stack won't have a mass. Cannon.js won't have any effect on them. They won't move unless we move them explicitly, like the way we did before. We still want to define them in the world of Cannonjs as well, because they will serve as obstacles. And the other case is for the overhanging parts. They will have a mass and Cannonjs will move them. And in our game logic, we won't change their position at all. So the 2 scenarios are that either we control a box and Cannonjs has no saying in it, or Cannonjs moves the box and we won't change it. These 2 cases conveniently cover 2 different kinds of boxes. When we create a box with the addLayer function, we will create a box with 0 mass. These boxes we will control. When we create a box with the addOverhang function though, the mass will be 5. These boxes will be controlled by Cannonjs. Once we define the body, we add it to the word object similarly as we add the mesh to the scene. And finally, we add it to the returned object as a property for further reference. Now you can see why did I call a property containing the mesh Three.js. Because we have a very similar thing also containing a box model, but used in a different way. So now we have a Three.js property and a Cannon.js property, clearly indicating which one is which. Whenever we change something, we need to keep Cannon.js in sync. Otherwise, it might happen that objects fall through objects, or they bump into invisible obstacles because we only updated the visual part and not the physical model. There are 2 spots that we need to adjust. One is the animation function. When we animate the top level box, we also need to update its model in the world of Cannon.js. The other case is a bit trickier. When we cut the box, its dimension changes. Earlier, cutting the top-level box into 2 pieces was part of the event handler function. Now it got a bit longer, so I moved it into a separate function. We can shift the position of the cut box the same way, but scaling is not an option in Cannon.js, so we need to find another way. Instead of scaling the body, we are going to remove the existing box from the body and add the new one that fits the size. So these were the 2 cases when we changed properties and Cannon.js had to follow. Now let's see the other case when Cannon.js is adjusting things and we have to sync these properties to Three.js. At every animation loop before rendering, we step forward in time with the physics simulation. We call a new utility function before rendering to simulate physics. In this function, we simulate time passing. The setAnimationLoop function, similarly to the requestAnimationFrame function, is running around 60 times every second. So we step forward time with 1/16 in Cannon.js. We could be more sophisticated and use the exact time passed, as the animation function receives it as a parameter, but the precision we gain with this is not significant. Now as we step time forward, Cannon.js updated the positions and orientations of the objects defined in its word. More precisely, it only changed the ones with a mass, because the ones without a mass are considered stationary. So the last thing we have to do is to sync these values from Cannon.js to Three.js to update them on the layout. We do this by going through the overhanging parts array and copy their positions and orientations. And if we did everything right, then we finally have a game. If you want to go through the code in more detail, then you can find the whole source code on CodePen. The link is below in the description. If you want to play around with the code, you can find a fork button at the bottom right corner that will make a copy for you of the game. This version you can change as you like, and your changes will be saved to your account. If you want to build up your very own Three.js game with cannonjs from scratch at CodePen, then you need to add these libraries first. When you start the pen, go to Settings, and on the JS tab, add Three.js and Cannon.js as external scripts. And now we reached the end of this course. If you like this course, please subscribe. I have some other Three.js game ideas I'm planning to cover, and I'm also uploading web development related courses on other topics. Let me know what would you like to learn next, and if you have any feedback for this video. Also, don't forget to check out my earlier videos on game development, like building a bridge building game with HTML canvas. See you at the next one.